All right. So next thing we're going to calculate is a weighted mean. So to calculate a weighted mean, and this is on your handout, this slide, we're going to do the sum of the products of the entries, which would be our data values, and their weights. And then we're going to divide by the sum of all of the weights. So things that are weighted, a common example is like GPA is something that can be weighted, or grades and classes can be weighted. Anything that a data value carries a specific weight can be calculated with a weighted mean. The formula that we use, you can see that X bar again, which means sample mean. And here's the formula that we're going to use, our sigma notation, so summation, XW, which means each X value times its weight, and then we're going to sum all those values up, divided by the sum of all of the weights, whatever those are worth. Okay. And that formula, and along with all those other ones, remember those are at the back of that chapter 2 packet that I gave you. So common example is grades, like our class. So homework is 25%, projects 25%, tests are 30%, and a final exam is 20% in a statistics class. It says at the end of the semester, Bob has the following grades. His homework is a 95%, his projects are an 82%, his tests are an 85%, and his final exam is a 64%. We're going to calculate Bob's final grade. And this is exactly how you could calculate your grade in this class. The first few columns that you guys see in Blackboard, those are your overall category weights, your overall project, your overall homework, your overall test. So you can do this at any time and kind of play with the final exam eventually to kind of see what your overall grade would be. It'll be a little bit prettier once you have a grade in for every category. Okay, so the first thing we need to do is we need for each category, for each data value, multiply Bob's grade times the weight that that category holds. Okay, so Bob's grades, let's start with homework. I'll do this work at the top here. So Bob has a 95 in homework, and the weight of his homework is 25%. Okay. And I'm just going to use 95 instead of 0.95. That way, whatever number I get out is just going to be a whole number score instead of a decimal. I just don't want to get a decimal at the end. Okay, and we're going to do the same thing for every category. So next, Bob has an 82 for projects. Projects are worth 25%. He has a 85 for tests. Tests are worth 30%, 0.3. And then he has a 64 for his final exam, and that is worth 0.2. Okay, so that is the numerator of that formula, the sum of all of our x's, Bob scores, times their respective weights. Okay. Denominator is the sum of all of the weights, which are the percentages that his grade is being calculated with. So 0.25 plus 0.25 plus 0.3 plus 0.2. And if you're calculating a grade correctly, in most cases, it should equal 1 at the bottom, representing 100% total. And then you just type it in your calculator. So like I said, the bottom is going to add up to 1. You can type in the top, and that's pretty much going to be our answer. You're going to need your calculator for a couple things. If you don't have it out already, you probably want to grab it. Okay, so if I get all that numerator calculated, I get 82.55, so Bob's final weighted grade would be 82.55% in the class. Okay. Questions on that one? Okay. All right, so I want you guys to do the same thing here for a GPA. So for a GPA, there's usually for a school, and most schools use something similar to this, a scale where a letter grade is associated with something on the 4-point scale. So if you get an A+ or an A, you get a 4-point. You get a C, you get a 2-point for that class. Then when you take a college class, every class is worth a certain number of credit hours. Like our stats class is worth 3 credit hours. So that means this class's grade has a weight of 3. Okay. So what you're going to do here is you're going to calculate Mike's GPA. So for example, for a B plus, he gets a 3.3, and that has a weight of 3. And you're going to do that for each of his classes, divide by the total weights, and figure out what his semester GPA would be. Okay? Go ahead and try it. Okay, whenever you're ready, check it. So I put my work up there. So I did what each grade is worth times the number of credit hours for that class. So for that B plus, it's a 3.3 times a 3. For chemistry, it's a 2 times 4 plus psych, 3.7 times a 3, etc. And then divide by the weights, which are pretty much the total credit hours that Mike took this semester. So he took 18 credit hours, do the division, you get 2.944. So you can see that C really brought it down because that's a pretty heavily weighted class. It's a 4 credit hour class, getting a C in that versus if I got a C in like a 2 credit hour class, it probably wouldn't affect my GPA as much. Okay. Any questions? Yes. Oh, I did. Oh, no. So it doesn't bring it down that much then. Good catch. So that's a 16 then, right? Why did I do that? I don't know. I was looking at the wrong number. How about 3.3125? Does that sound better? Okay. It's early. Thanks. All right. Any questions on that one? Okay. The last couple charts that are on your paper are going to be finding a mean with a frequency table. And you guys had one of these yesterday, but it can get a little tedious if you have a frequency table to use every single number multiple times, especially if something has a frequency of like 15. We don't want to type a data value in 15 if we want to calculate the mean. So this is a little bit hard to see, sorry. So that's x bar is equal to the sum of our x's times their frequency divided by n. Okay, so if we have a frequency table, instead of listing each x value out multiple times, if we know it occurs at number of times, to calculate that sample mean, we can take each x value and multiply it by its frequency and sum all of them up. So this is kind of going to look like what we did with the weighted mean. We're going to take each data value and its frequency is kind of like its weight that we're using. It's how many times that data value occurs, divide by n, how many data values we have total, and that gives us our sample mean. So we're going to do that in this table to the side here. So we have times and we have the frequency of each time. So if you wanted to, you could take those times and you could put 10 3 times, and you could put 11 there 5 times, and you could put 12 twice, so on and so forth, but that's a little tedious. So we use this instead. We're going to take each time, which is our x in this problem, and multiply it by its frequency f. So we're just multiplying the two columns together. So that's going to give me 30, 55, 24, 26, 14, and then we're going to sum all of those up. We're going to sum up all of our x's times their frequency. So 30 plus 55 plus 24 plus 26 plus 14, I get 149 is this the numerator. Okay. Then I need to divide that by n, where n is the total number of times that I have. So to get n, you're just going to sum up those frequencies, how many times each number occurs. So 3 plus 5 plus 2 plus 2 plus 1 gives me 13. N is 13. So 149 over 13. My sample mean, my x bar, is about 11.46 if we give it a couple decimal places. Okay. Make sense? So that can save you a little bit of time if you have data values that repeat. Instead of adding it up multiple times, you just multiply it by the frequency. Okay, the last one that you have in your handout there is similar. We have a frequency table here, but we have a bit of an issue. So here it's cappuccinos and frequency of the cappuccinos, but when I see that 2 cappuccinos are between the values of 0 and 3, I don't have their exact numbers. I don't know if it's a 1 and a 3 or a 2 and a 2. We don't have the actual data values. So if that's the case, how we calculate the grouped mean is we use the midpoint of that class. So like the midpoint of 0 and 3 would be 1.5. And we use that as the data value for that row. Okay, midpoint of 4 and 7, 5.5. Midpoint of 8 and 11, 9.5, 13.5, 17.5. Okay, and then that's going to be our x that we're going to use and our f that we're going to multiply together to get that last column. Okay, so 2 times 1.5 gives me 3. 3 times 5.5 gives me 16.5. 8 times 9.5 gives me 76. I'm doing this in my head. Tell me if I'm wrong. 3 times 13.5 gives me 40.5. 2 times 17.5 gives me 35. Look good? Yeah? Okay. Add them all up. Let's get our totals. So if I add up those frequencies times the midpoints, 76, 40.5, 35, I get 171 is a sum there. Sum of my frequencies, again, is going to give me n. So 2 plus 3 plus 8 plus 3 plus 2 gives me 18. To find my sample mean, my x bar, 171, which is the sum of all the x values times their frequencies, or in this case, the midpoints times their frequencies, divided by the sum of all the frequencies, which is my n. So 171 over 18, 9.5. Okay. Questions getting a group mean, weighted average. Okay. The last 2 slides on here, you might want to draw a picture or put something on your definition sheet. So when we start talking about all of our charts and graphs, especially like these pictures are all histograms, they're going to ask you what type of distribution it is, and they're just asking what kind of shape the graph has. So there are 4 shapes that you're going to want to know. The first is symmetric. So symmetric is exactly what it sounds like. You can draw a line right down the middle and it looks the same on either side. So a lot of times we have kind of this hill shape. We're going to eventually call it like a bell curve. It doesn't necessarily have to be this shape though. It could maybe be high on both sides and dip in the middle. As long as it's the same on both sides, if you can draw a line down the middle, it looks like a mirror image, you have a symmetric distribution. When you have a symmetric distribution, your mean, median, and mode are going to be pretty much in the middle, all in the same location. So if you're not sure what kind of distribution you have, you can look at those values for mean, median, mode, which is why this pops up in this section, and determine that. Okay. Uniform distribution is sometimes called a rectangular distribution. You can see why it would be called a rectangular distribution. It looks like a big rectangle. Pretty much every class has the same frequency across the board. Okay. This one, again, the mean and median are in the middle, but in this case, we don't really have a mode. We don't have one data value that stands out a whole lot more than the other ones. So that's also a clue that you would have a uniform distribution. If you don't have a mode, or maybe you have a lot of modes, like if you have 7 modes, it might be a uniform distribution. Okay, so symmetric, same on both sides, mirror image. Uniform is rectangular, straight across. Okay. The last two are going to be the ones that are going to show up if we have skewed data, we're going to call it. They're going to be skewed in one direction or another. So the first one is skewed left. We also call this negatively skewed. If something is skewed to the left, its tail is to the left. So if I were to kind of draw over this picture, I would have a tail going out on the left side. It's going to be, most of my data is going to be on the right side of the picture, and then it's going to get smaller and smaller on the left side. So that's how we know we have a left skewed or a negatively skewed set. Also, if you look at that little piece of information at the bottom, your mean will be lower than your median and probably your mode. Okay, so if the mean is smaller, it's because my data values are being pulled in that direction. Maybe there's an outlier down there that's getting us that negative tail. Okay, and then right skewed, positively skewed is exactly the opposite. The tail is going to be to the right. Okay, so if I trace over that, it kind of levels out, and I've got some data values that are on their own on the high end. And in this case, the mean is going to be on the right side. Okay, so if you're not sure which way it's skewed, look at where the mean is. If the mean is to the right or the tail is to the right, it's right skewed or positively skewed. If the mean is to the left or the tail is to the left, it's left skewed or negatively skewed. Okay, and then that's it for the 2-3 lesson once you guys have all that written down. That's just stuff we didn't get to yesterday. 2-3 Math Excel. Let's see when that's due. Which one's you guys? 2-3 is due tomorrow night. So you guys have tonight and tomorrow to work on that one. I also have for you, if you are interested, a bonus opportunity. That's that out when you're writing that down. So this is called a circuit training. Any of you guys that have taken college algebra trig last year, you guys did these quite a bit. If not, I will explain how these worksheets work. So this is kind of an all-encompassing review of everything from chapter 2. Now, a couple of these things we haven't done yet. We're going to get to standard deviation and box and Whisper plots in the last 2 sections, but they'll be coming up soon. This is worth 2 bonus tickets on your upcoming test, and it is due on February 14th. Well, hold on, let me double check that before I say that out loud. Did I put it on here? No, it's due on the 11th for you guys, if you want to write that at the top, February 11th. So how a circuit training worksheet works is you're going to start in box number 1 at the top. You're going to do that problem. The answer to that problem is located somewhere else on the worksheet. So maybe the answer to that problem is 79. Okay, so that would be at the bottom of the first page. So then that box would be problem number 2, and I would do that one second. And eventually, if you do all the problems correctly, you get to every single problem, and the last problem takes you back to the first box. So option number 1 is you can do the problems in order. Do a problem, find the answer, do that problem next. Option number 2 is you can just do all the problems and then go back and put the numbers in at the end once you have all the answers. But if you have an answer that's on the worksheet somewhere, that's probably a good sign. Right? Okay, so due next Friday. This is bonus, it is optional, but it's a nice little practice with everything that we're doing in chapter 2. Okay? Questions on that? Got it? Okay. All right. odds for snow days for sure?
Well, Thursday is probably at least 95.
95 for Thursday right now? I saw in the news this morning, I live in Akron, and they're saying it's going to be a lot worse there than it is down here, so I might have a rough drive to work if we don't fall off.
So bad.
What do you think the odds for Friday are? We have odds for Friday yet? Thursday's better.
Yeah, because Wednesday's going to snow.
I know, but it's not going to get like icy or anything until later in the evening on Wednesday. Oh man, if you had both days. Do you know what my favorite snow day is? It's the one that we know the night before, and you can turn your alarm off. You don't have to wake up in the morning. That's what I'm looking for. And then you can make plans. Yeah. Well, if we have a blizzard, you can't really make plans. Your plan is just to sit in your pajamas and catch up on this kind of stuff. Okay. I will be at home in my pajamas. All right, let's see what we got here. 2, 4. We'll do a little bit today. Start it. Let's see. All right, so we're going to talk about measures of variation. Mostly standard deviation is the big idea that's going to come out of this section, and we'll be using that quite a bit throughout the semester. I will show you after we're done with this lesson tomorrow how you can find some of this stuff in the graphing calculator. As far as tests and things go, you are not allowed to use graphing calculators on any test all semester. That's a Stark State rule. But you can use it for projects and things. So I am going to show you how to do some things in the calculator that are going to make your lives a little bit easier where we can. Okay. All right. So first definition officially is range. We saw this definition before when we were talking about our frequency tables at the very beginning of 2.1. Range came up, right? So I don't know where it's on there. You guys probably know this definition anyway. So range is just our max minus our min. That's what you need to know from that. Max minus min. Okay. So for example, here I've got a bunch of salaries. They're in thousands of dollars. If I wanted to calculate the range of that, I would just need to find the maximum value and the minimum value. What's the maximum value in this little table here? 47. What's the minimum value? 37. So 47 minus 37 was going to give me what? 10. So technically that represents $10,000 is the range of the salaries. Okay, good. Nothing crazy there. I know you guys have done that before. Max minus min. Okay, so we're now going to start talking about what we call deviation. Deviation is how far a specific data value deviates, varies from our mean that we're calculating or that we have for that data set. Okay, if we're talking about a population deviation, we're going to be using this formula here, x, where that's any data value in our set, minus mu. We saw that symbol yesterday. That would be the mean of the population. If it's a sample deviation, I can't remember if I have this on another slide or not. It's x minus x bar. Okay, so just different symbols, that mu and that x bar, they both mean the mean. It just is going to look different based on if we have a population or a sample. Okay, so here we have a dot plot. It represents height of macaws at the Columbus Zoo, and everything's measured in centimeters. So what we want to do is we want to list the heights in our table. If something occurs more than once, we're going to list it more than once, and we're going to find the deviation for each height. So how far it varies from the mean of the sample that we're going to find. So we'll need to get that in a minute. Okay, so let's go ahead and just list out all the heights that we see in the dot plot. So my first one is 69, then I have two 70s. My next one is 72. 73, 74, then I have a 77, 2 78s, and a 79 are all of my heights. In order to get the deviation, I first need to find the sample mean. So, we're assuming it's a sample here. Okay. Unless we know it's all the macaws. They didn't say that, so we'll just say sample mean. So we're just going to add up all our heights and divide by how many macaws there are. So if I add up all my heights, 69, 70, 70, 72, 73, 74, 77, 78, 78, 79, I get 740. Divide by how many there are, and I think I have 10. So my sample mean for this data set is 74. Okay, so my heights are my x's. My deviation, to calculate that, we're doing x minus x bar. So if I do 69 minus 74, what do I get? -5. And our deviation could be positive or negative. A negative deviation tells us it's lower than the mean. A positive deviation tells us it's higher than the mean. 70 minus 74, -4. I've got a couple of those. 72 minus 74, -2. 73 minus 74, -1. 74 minus 74, 0. So 0 tells us it doesn't deviate from the mean. That is the mean. 77, 3. 78 is 4. And 79 is 5. How you know if you got all your deviations right? Sum up that column real quick. -5 plus -4 plus -4 plus -2 plus -1 plus 3 plus 4 plus 4 plus 5. And you will always get a sum of 0 if your deviations are correct. Okay? Questions calculating a deviation. Great. Okay, so now definition of a variance. So at the bottom here, this is going to be our variance formula. At the top first, we have a definition for what we call sum of squares. Sum of squares is kind of what it sounds like. We're going to take our deviations that we just found, we're going to square them, and then if we want the sum of squares, we add those all up. Okay. Here is the formula if it's written with population. It may also look like this if it's a sample. Okay, so again, the only thing that's different is that mu is changing to an x bar if we have a sample set versus a population set. Sum of squares. Then we take that one step further to find population variance. And it's really finding variance. This formula is how it's written with population, and I'll write it down below in a second with our sample. Actually, I might have that one on another page for you. The numerator, that's that sum of squares. So we've got our x minus our mean squared, and then they're summed up. And again, that mean is if it's a population, divided by n. It's a capital N because it represents our population number. If it's a sample, it's going to be a lowercase n. And then this symbol is sigma, so it's the same symbol as this guy, it's just a lowercase letter in our Greek symbols. So sigma squared. If we have a sample, I think we use S. Let me double check. Hold on. I have that later. Oh yeah, we use S. Okay. Sum x minus x bar squared over our lowercase n. So this is population, how to look. This is sample, how it'll look. Same formula, couple different letters again, if I have a population versus a sample. So there's several steps to this formula. You're going to find your mean. You're going to find all your deviations like we found on the last page. Then we're going to square all those deviations. We're going to add those up and divide by n how many data values we have. This is one step away from our standard deviation that we'll calculate then. Okay, because there are several steps in the process, a lot of times when we calculate standard deviation by hand, we're going to create tables like you can see on your paper that we're about to do. Okay. Yes.
Would that be sample variance?
Yes. So population variance is at the top, sample variance at the bottom. Okay. You got it? All right. Standard deviation, all we do is take it one step further. If you look at the formula down here, I don't have my sigma squared anymore. It's just a sigma. And over here, I've taken the square root. So it's pretty much the variance formula. We took the square root on both sides. This gives us population standard deviation. We will also have sample standard deviation, which looks like the following. Again, similar formula, just some different variables. X minus x bar squared over n. So we find our sum of squares. We divide by how many data values there are. That gives us variance. Square root of variance gives us standard deviation. Okay, so what is standard deviation and why do we care about it? Because we're going to be using it a lot. So standard deviation measures the variance of a data set about the mean. So if something is within one standard deviation, that means it's close to the mean. If something is within 2 standard deviations, it's further out. If something is within 3 standard deviations, it's further out. And it tells us how far we have the spread of our data. Variance and standard deviation will always be a positive number. Okay. As the entries get further out, our standard deviation or our variance increases. So if I have a very large spread in data, my standard deviation is a big number. If my data is very close together, my standard deviation is a small number. Multiple standard deviations mean that data value is further away from the mean. Less standard deviations tells me that my data value is closer to the mean. And we'll talk a lot about how to figure out how far a data value is from the mean, how many standard deviations, but for right now in this section, we're just going to be talking about how to figure out what that standard deviation is. But you need to remember standard deviation means how far we have our data values spread out from one another. A bigger number means a bigger spread in the data. Okay. All right. So let's look at your table on your paper, and this will probably be our last one for today. Okay. So we're going to take our salaries here, and we're going to calculate variance and standard deviation. All right. So starting with variance. We first need to order our data values. Probably that'll make our lives a little bit easier. This is salary in thousands of dollars. We can keep the zeros off of it and just remember at the very end everything's going to be in thousands. Okay, so my smallest number here is a 32. Just cross out things as I go. 38, 39. I've got 3 41s, a 42, a 44, a 45, and a 47. Okay, those are your X's. Let's, for right now, assume that this is population. So I'll use those variables. To find deviation, we're going to do X minus mu. X minus mu. Okay. So to find mu, that represents the mean of all of our data values. We're just going to add them up, divide by how many there are. So 32, 38, 39, 41, 41, 41, 42, 44, 45, 47. I get 410. Divided by 10. My mean for this population is 41 or 41,000. Okay. So now we're going to take each of those x's and subtract my mu. 32 minus 41, negative 9. 38 minus 41, negative 3. 39 minus 41, negative 2. 41 minus 41, I'm going to have a bunch of zeros. Then I'm going to have 1, 2, 3, 4. Nope, that's wrong. 1, 3, 4, 6. There we go. And if you want to double check at the end, all those deviations should sum up to 0. Okay. Now we're going to take every deviation and square it. So this is this part of the formula, x minus mu squared. So all I have to do is negative 9 squared. You can do that in your head. 81. 3 squared, 9. 2 squared, 4. Everything's positive when we square it. We don't need to worry about negatives. 1, 9, 16, 36. Sum up that column, and that is the sum of our squares. So 81, 9, 4, 1, 9, 16, 36. I get 156. All right. So to find my variance, I have everything I need now. Variance is the sum of my squares divided by n, where n is the number of data values I have. Well, the sum of our squares was 156. That's what the table helped us get. Divided by n, number of data values 10, and I get 15.6 is our population variance. Okay, so 15.6 thousand, 15,600, if I were going to give that a number to represent what this data stands for. Take it one step further and you get standard deviation. Standard deviation is just that same symbol without the squared. So we're going to take the square root of our variance. Square root of 15.6. And I get 3.95 is the standard deviation. So that means if I am within 1 standard deviation of my mean, I'm about 4 units higher or lower than that average. Okay, or if I'm within 2 standard deviations of my mean, I'm about 8 units above or below my average. That's what that tells me. It tells me how far spread out my data is. All right, we're going to stop there today. Tomorrow we'll just do a few more examples with standard deviation, add in the last couple definitions, and wrap up 2-4. We're not going to start 2-5 tomorrow. Okay? So just be working on that 2-3 homework tonight. Let me know if you have any questions. You can start working on the bonus if you want as well.